By way of introduction, I'm Maria Juenger. I'm a professor at the University of Texas at Austin in the Department of Civil, Architectural, and Environmental Engineering. My background is in chemistry and material science, so my research expertise is on the chemistry and material science of cement and concrete. But what I want to talk to you today about is some things that have been referenced already today that have to do with the energy and CO2 implications of the cement industry, but also a little more detail on what we mean by process emissions versus emissions that are coming from fuels. And I did couch all of this in terms of global numbers, but we can also talk a little bit about how that relates to the US, as was mentioned earlier too. So I have fun facts to start with because I think that's entertaining. So fun facts and fun pictures. Concrete is the world's most used material. So many of you already know that. It's 17 to 20 billion metric tons of concrete that are produced per year globally. And then in terms of what this means when we're talking about in cement and concrete, I have this cute little picture of what a sack of cement is. And in the US, there's still a lot of discussion about cement in terms of kind of archaic terms of sacks that are 94 pounds each. And these would go into a concrete mixing truck. And yes, they use American units that would contain, for example, 7 to 9 cubic yards of concrete, so by volume. So when we're talking about a concrete mixing truck that's driving down the road, that's something like, let's say 8 tons of concrete that are in that particular truck. So just for context, that 8 tons, turn that into 20 billion. And then in terms of the cement that's produced per year globally, we're making on the order of 4, maybe a little more billion metric tons of cement that are a component of that concrete mixture. And that's what we're really going to be focusing on today. The fun fact that that I've seen about this that I really enjoy is that it's 626 kilograms per capita. So we're making more cement than we're consuming food as humans. So these are global numbers. It was mentioned earlier, I think Mark Johnson mentioned earlier, that the US numbers are small compared to other countries. I would say that yes, China is contributing in many cases up to half of this, maybe a third. The US is certainly smaller, but the US is a huge contributor to this number as well. We shouldn't minimize the role that the US cement industry plays. It's still significant compared to many other countries. Okay, so we know that the cement manufacturing process itself is extremely energy intensive. So to produce 1 ton of this Portland cement, we need 7,000 megajoules of electrical power and fuel energy. And as you can see on the left, a lot of this is what we use for kiln fuel. So the amount of energy, 86% of the energy that we're putting in to produce a ton of Portland cement is going into kiln fuel. And the diagram on the right shows this process where the materials themselves are the raw materials are inserted in the top left and go through a process of preheaters through this kiln to the output. And the fuel is on the far right of this process, is where we primarily have our fuel source. And the need for that fuel is to create a high temperature. I wrote 1450 degrees C here. It could be 1350. It just depends on the particular plant. But what I want to show with respect to this diagram as well is you can see that the flame, this is a diagram, you can see that the flame is actually part of the kiln itself. So I want to stress that when we're talking about using fuel for the cement industry, we're talking not just about having a high temperature, but that this fuel in some ways gets integrated, the byproducts from this fuel, what's coming off of it in terms of particulate matter, but also volatilized gases, actually combine with the product that you're creating. And so the source of this fuel becomes important when you're considering the quality of the product that comes out. And so that's why I wanted to make sure that I showed a diagram that contained fire. Okay. The other thing that's been talked about a little bit today is what we mean by process emissions. So the cement manufacturing industry uses a lot of energy. It also produces a lot of CO2. And the other fun fact that I love is this one that says, if the cement industry were a country, it would be the 3rd largest emitter in the world behind China and the US. So I find that really just remarkable and shocking, though I think it's probably not as shocking to this audience here as to some others. If we look at these CO2 emissions, you can see that it's broken out into what we're calling process emissions and what we're calling energy emissions from the use of energy. So the thermal emissions from the kiln fuel, and then the electrical emissions from other types of processes or other transportation related emissions are less than 10%. The process emissions come from the fact that when we make Portland cement, we use limestone as our primary raw material. And so we're using a lot of limestone. When you heat that limestone, you heat it up and the carbon dioxide is removed, so you create calcium oxide, which then reacts with silica, which is another raw material, to create the cementing phases that are in our clinker, so the necessary products. So when we're talking about energy and CO2 implications, it's important not to just look at the fuel that we're using. It's important to look at the chemistry of this process as well to see if we can alter that, in addition to altering the temperature processes. So there are many, many agencies that have started looking at what can we do to change carbon emissions, what can we do to reduce energy. So there's been several studies that have been published on this, and you can kind of break them down into something that would require a change to the way the manufacturing process is operated. And so I wrote that as equipment and process changes. So not to be separate from process emissions, just the process of manufacturing. And so we can try to work on the thermal and electric efficiency. We can start considering the use of alternative fuels. A lot of this has been discussed already today. But we can also look at what if we change the chemistry of the system itself. And this is something very different from what we've talked about today, because, for example, in the earlier discussion of ammonia, the end result is you're still producing ammonia. In the discussion of steel, the end result is you're still producing steel. With the cement industry, we have the opportunity to not produce cement, to produce something else that we can use to make a concrete, alternative materials. That's a quite very different opportunity than what we have in other industries. And so I'm going to talk a little bit about that today in the context of what those opportunities are. We also, as Marlena mentioned, the idea of carbon capture and storage. We have some unique opportunities in the cement industry where carbon capture and storage can certainly be done as part of the cement plant operations, but we can also consider carbon capture and storage into the material itself. And so there's some material changes that can happen there. And the fifth always, and Marlena also mentioned this earlier, efficiency of materials use or materials changes. I'm not going to talk about this today because that's a subject of a later workshop, but I'm going to talk about these first four topics in a little more depth and what the opportunities are for research in these areas and for industrial changes. So many years ago, I sat in a seminar and somebody pulled up this Eisenhower decision matrix, trying to help people think about how to spend their time. So if something is urgent and important, you get it done right away. If it's important but not urgent, you plan ahead, make a to-do list, et cetera, et cetera. Many of you are familiar with this. But what I like to use this for is to change it up a little bit, because we can use the same sort of decision matrix to think about how to prioritize research. And so when we think about research, for example, if something's urgent and important, that means that it's, at least from an engineering perspective, ideas that have rapid implementation potential. So these are things that are urgent to work on because you can have an impact from them right away. But if we think about things that are important but not urgent, we still need to work on those. Those are critical in terms of investment of research efforts and dollars. But we might not see an impact for them for many years in the future. So these are ideas with long-term potential. Where the sort of Eisenhower decision matrix falls apart is if you're making decisions and you have something urgent and not important, it says to delegate. Anything that's urgent but not important is just a distraction, and we shouldn't be focusing on it in research at all. So if it's not important, it shouldn't be done. The same with not urgent, not important, you get rid of it. It is a bad idea. So in terms of this, what I like to think about is, can we take these levers for change and categorize them into the two different categories, ideas with rapid implementation and ideas with long-term potential. So in terms of those first four levers, really what I think is important here is thermal and electric efficiency. That's something that's relatively straightforward in this type of industry, and we can adapt advances from other types of industrial technologies. Clinker substitution, parts of clinker substitution, some aspects of the clinker substitution, the changing the type of cement we use, are ideas that can be done right away. Some are not. But the ideas of carbon capture and alternative fuels, those are ideas with long-term potential. They're things we need to work on and focus on. They have a big impact, but they're going to take a longer-term investment into those types of technologies. And what I'll say right now, in terms of the way the US is investing money into research in the world of cements, is really primarily most of what the US is focusing on is the clinker substitution. I would say most research efforts are focused in that area and far less on the other types of topics. This is again just something from the news that sort of gives the possible impacts of CO2, of these types of levers on the actual reduction of CO2. And this is in percentage. So, take this for what it's worth. But the reason that alternative fuels and carbon capture and storage have good long-term potential is we can get significant reductions in CO2 from these strategies. Novel cements and clinker substitution, this idea of using something other than cement, can also be extremely, have an extremely high impact, whereas the energy efficiency has less of an impact. There's another study that's come out of Germany that's looked at this as well. And again, they're stressing innovative technologies, carbon capture, other types of changes to equipment itself, whereas looking at the cement systems is less of a contribution, but still important. And that thermal and energy efficiency, again, is kind of a small contribution, not to be ignored, but not as important. So I'm not going to spend a lot of time on, I'm not going to spend any time on thermal efficiency because it's such a small piece of this puzzle. So it's something that can be done when changes are being made in cement plants anyway, but it's something that is certainly achievable, but the impact is small. The concept of alternative fuels are really quite important though. And what you can see is that in other countries, they're taking a lead compared to the US. Other countries are taking the lead and actually reducing the share of fossil fuels used to fire cement kilns and increasing the share of alternative fuels. And usually what's meant here is not necessarily what we've already discussed today. It's usually things like waste solvents or waste solids from other industries that are being used, which come with their own challenges. So for example, if you have a waste solid that has a high moisture content, that affects the way it's being burned to create the fuel. And then we also have to take into account this concept of contamination. So contamination from what you're burning into the cement process itself. And there's lessons to be learned historically from that that need to be considered in this change or push toward using alternative fuels. In terms of clinker substitution, and so this sort of goes into the area of research that's my specialty, which is when you are making concrete and you're adding Portland cement, aggregates, water to a concrete mixture, the amount of that cement that goes into that concrete mixture is variable. And so that cement can be variable because you choose to use less. That cement can also be variable in terms of material efficiency. The cement content can also be variable because you're replacing a portion of the cement with something else that can provide what we call cementitious or binding capacities in the composite material. And so if you look at this plot here, there's a red line showing Portland cement that's used annually, and there's all these other possible materials that can be used to partially substitute that cement. This is widely done already in the US, but if you look at the bullet item up there, more than 60% of concrete in the US uses it. We can increase that number to 100%. That's relatively straightforward. That's completely low-hanging fruit. There's research efforts funded to try to make that process predictable and efficient and to try to explore some of these newer sources of materials that we can exploit. Right now in the US, primarily the substitute material that's actually used is fly ash from coal burning. We know where that's heading. The industry is prepared is already investigating and developing substitute materials for the fly ash in order to continue this process of clinker substitution. So we use less cement, we use in our concrete, we make less CO2. The other type of option in terms of clinker substitution, and clinker being the Portland cement material that's in a cement, is what we call alternative cements. And what this is a little more ambitious. And the idea is we've been using Portland cements for 150, 200 years. Why don't we use something else instead that doesn't produce as much CO2, doesn't take as much energy to produce in manufacturing? And some examples of these types of materials are what we call geopolymers or alkali activated materials, calcium sulfate aluminate belite cements, magnesium-based cements. And so they're being explored industrially and in research processes. The picture on the right looks really boring compared to the one on the left, which is, an industrial, is a Lafarge Wholesome product. The one on the right is a alkali activated geopolymer bench that we actually made in my lab a couple of years ago as a demonstration for a hotel. Just to show that the material looks, feels, behaves just like a normal Portland cement concrete. I don't think they liked it that much. I think that's an emergency exit or something like that, or a smoker's area. But these materials are feasible for use. But one of the problems with them is that they tend to be used in niche or fringe applications. Because if you look at the pie chart on the right and the abundance of elements in the Earth's crust, silicon and oxygen are by far the most abundant materials. Calcium is pretty high, aluminum's pretty high. We're already using iron. We're using these in Portland cement anyway. If we start going to magnesium or other materials, it's necessarily going to be harder to make something on the scale of the 4.6 billion tons of cement that we need to create. So that's something to consider. Another consideration with alternative cements is as we start going into materials that we perceive as being producing less CO2 because they have less calcium, we actually need to do the calculations in terms of the CO2 emissions to understand how much of a reduction we're actually getting, because some of these systems may be more complicated, more expensive, harder to introduce to the industry because their performance characteristics are different. So that if we make a big change, we have to ensure that that change actually results in CO2 savings that warrant the change to the entire industry. So it's a bit of a tricky game. So there's a lot of research opportunity in this particular area as well. In terms of carbon capture, this is something that I would say is being explored to a lesser extent in the US than other countries because of the carbon taxes and other things that are implemented in other countries. And so there's a lot of technologies available. This is a slide that I've taken from a student who did a senior thesis on this topic last year. And some of the technologies that people are looking at implementing directly into a cement plant are the concept of amine scrubbing, calcium looping, and oxyfuel combustion. And there are actually plants in Norway, Taiwan, and in the European Union and other countries that are actually implementing these in plants. The cost is quite high to do these technologies, but in the long term, with improvements to equipment, should be able to decrease over time. So this is a great opportunity. I would say less in terms of research, but more in terms of implementation and industrial implementation. Another unique opportunity with cements, and I wanted to bring this up, is the concept of carbon capture is not independent from the concept of changing the cement material itself or creating an alternative cement. And so there's a unique opportunity in the cement industry to do both at the same time. So there's a lot of research opportunity, as I mentioned, in alternative cements, but also in alternative cements that actually capture CO2 as part of the mineralization process to make the material. And so these are just two examples of companies that exist that have a process that takes CO2, mineralizes it, and turns it into a building product itself. So there's a lot of unique opportunities here to look at it. I would say instead of just looking at the energy perspective, to look at a bigger picture. And a bigger picture includes both the material and the processing at the same time. Okay, so in conclusion, I think that the cement and concrete industry are the most important materials for development of infrastructure globally. There's no argument there, but also in terms of the US, in terms of infrastructure expansion and renewal. The energy and CO2 footprints are large, but we have a lot of different opportunities and very different types of strategies that we can use to reduce those emissions, from the fuels to the technology in the cement kiln to the materials themselves. And it's important when we're thinking about funding directions in the future to consider both short-term and long-term solutions simultaneously, so we can hit the easy parts and the more difficult parts in good time. Thank you.